How you doing? I'm Mr. Rose, and today we're going to talk about two things. First, Newton's universal law of gravitation, followed by Coulombs' law. Now, even though one of these is a gravitational attraction or a gravitational force, and the other one is an electrostatic force, they're very, very similar, so we learn about them at the same time. So let's first take a little bit of a step back and talk about Newton's universal law of gravitation. Now, we all know that if you stood here on Earth and you just dropped something, it would fall straight down. So instead of dropping it, if you took something, you threw it, it would fall in a parabolic motion to the Earth. If you did it again, threw it faster, it would go a little bit further, still falling down to the Earth. If you threw it at some point so fast, it would stay around the Earth and come back and smack you in the back of the head. That's what we call orbit. Now, Newton looked at the moon in the same fashion as he looked at things falling down. And he made this analogy. He said that if you take something, you throw it fast enough, like the moon orbiting the Earth. In fact, the moon is in a constant falling towards the surface of the Earth. Just like this ball was in a constant falling that you threw. The faster you threw, the further it went, but it always kept falling down. Now, the reason this happens is we don't like to think things as falling down. We actually, rephrase that, we think of things falling down. But what's actually happening is we have one mass, the Earth, attracting other masses. What I have here, all of these lines spread out, here's another picture of the Earth. All of these lines are gravitational field lines. And what that means is these represent the direction that every mass will go in the vicinity of the Earth. In other words, the Earth is attracting all of these masses down, which is why if I take this marker and I drop it, you see it fall down off of the screen. So, with that said, it's not just using this local equation to figure out the attraction to Earth or the force of gravity. This we call as a local equation. If I wanted to figure out my weight or your weight or the weight of this marker or the weight of this board, we're going to use Newton's second law. F net equals mass times acceleration, where we have some specific forces. F net, we really are talking about the gravitational force. And A happens to be the acceleration of gravity here on Earth, which is 9.8 meters per second squared. But notice, we don't actually have the Earth in this picture. So to take a bigger step and talk about what Newton was really doing, Newton said that you or any mass is actually attracted to the surface of the Earth. And it's attracted to the surface of the Earth with this complex equation, capital G, mass 1, mass 2, divided by d squared. What that says is this capital G is a constant, and during Newton's time, he actually didn't know that constant. This was figured out by someone by the name of Henry Cavendish. But he knew this constant existed, and it's a very small number. G is 6.67 times 10 to the negative 11th Newton meters squared divided by kilograms squared. Now that is a universal constant, which means it is the same every single place in the solar system, in the galaxy, in the universe, everywhere. It's always, always the same. Unlike the acceleration of gravity here on Earth, which is 9.8 meters per second squared. We know the acceleration of gravity on the moon, for example, is 1/6 of that. So this number never changes, so we can use it all the time. So let's do a simple example that we've done a bunch of times before. What would my weight be in newtons here on Earth? Normally, I would do F equals ma, so let's just do that right here. I would normally say the force due to gravity on Earth is my mass times the acceleration of gravity. Now we see over here, mass of Rose, I said that I'm 65 kilograms. So I would say the force due to gravity is equal to 65 times 9.8, that's the acceleration due to gravity. And when I multiply those numbers together, which I have done already, you get 637 newtons. Now again, that's local. Now maybe I want to do things more complicated, or again, we need to start to use this larger equation. So, the same example, what is my force due to gravity here on Earth? My mass is 65 kilograms. You need to know some other information, like the mass of the Earth, because the Earth is what is pulling me down to it. This is why we don't fall into other people when we fall down, because the Earth is so big. So the mass of the Earth is 5.98 times 10 to the 24th kilograms. And the radius of Earth, because we know that all objects will pull down to the center of Earth. So that radius is, if I'm standing on the Earth's surface, from there all the way to the center. And it's an average because we know the Earth isn't a perfect sphere. So the average radius is 6.38 times 10 to the 6 meters. Now we're going to follow the same examples we've always followed. The force of gravity is G, the mass of me, the mass of the Earth, divided by d squared. I need to write that formula. Now I'm plugging in numbers. Now this number is 6.67 times 10 to the negative 11th. You don't need to memorize that. It's on the MCAS formula sheet. I write that times 65 times 5.98 times 10 to the 24th. Divide that whole thing by the distance from me to the center of the Earth, 6.38 times 10 to the 6th squared. Now this may take you some time on your calculator. I want you to try this to make sure you can use all of these scientific notations. My advice to you is do the top and then do the bottom separate. If I do all of that, I should get 636.9 newtons. Almost exactly what we got here, 637 newtons. So this is a really powerful equation, and it's going to help us as we go forward with our Coulombs law, or electrostatic force. Okay, so next up is our electrostatic force, or Coulombs law. Here you can say I have drawn 3 different arrangements of just charged objects. We know that if I have a positive charge near a positive charge, those 2 objects, or a positively charged object, those 2 objects will repel, like so. We know because of Newton's laws, Newton's third law specifically, that force and that force have to be equal and opposite forces. 2 negative charges, what are those going to do? Well, a negative and negative like charges also repel. So my negatively charged objects will repel. Last, I have a negative and a positive. What will a negative charge and a positive charge do? Those 2 objects will attract. Because we've learned that opposite charged objects repel, opposite charged objects repel, like charges attract. So we just got through talking about Newton's law, and I wrote, this is kind of hard to see, I rewrote Newton's law below. Newton's law tells us that for any 2 objects, 2 masses, those 2 masses will attract, and they're going to attract because of the formula F equals G, mass 1, mass 2 over d squared, where G was a constant, M stood for mass, and D stood for distance. Now those forces are always attractive. Well, the electrostatic force and Coulomb's law, Coulomb was another scientist, and again, back in this time, we really knew things because of observational science. So Coulomb took everything that Newton did and said, well, this seems to make sense. And we use that planetary model, that law of gravitation, very similarly, which is why you should see a very similar pattern here. Coulomb's law, the electrostatic force, he said, was equal to some constant k, just like G's different number. Some constant k times Q1 times Q2. That Q1 and Q2, Q stands for charge, divided by a distance squared, the distance between those 2 charges squared. The laws are seemingly identical, where m, mass, is a property of nature. Every object has mass. Well, every object is made of atoms. You know atoms are made up of protons, electrons, and neutrons. Therefore, every object also has charge. Sometimes the charge is 0 or neutral. Sometimes it's not, like when I charge an object. So Coulomb took everything that Isaac Newton did and related it to electricity. So he said that K, which is an electrostatic constant, we don't need to memorize that. That's on our MCAS sheet too. 8.99 times 10 to the 9th Newton meters squared divided by Coulomb squared. D still stands for distance, and we have 2 objects, 2 charges, Q1 and Q2, where Q stands for charge. Now the unit we use for charge is a Coulomb, named after Coulomb, who discovered this electrostatic force. So for a simple example, we've talked about the atom, and we know Bohr's model of the atom worked really well for hydrogen. So here I have a very rudimentary picture of a hydrogen atom with a proton in the middle and an electron orbiting around. Now we do know still to this day that the average distance between the electron and this proton is approximately 5.29 times 10 to the negative 11th meters. That is a fact. We know the charge of an electron is negative 1.6 times 10 to the negative 19th coulombs. Previously you knew this as negative 1. We know the charge of a proton, those 2 things are the same size charge, just opposite. So the charge of a proton is 1.6 times 10 to the negative 19th coulombs. Like I said, the electrostatic constant, 8.99 times 10 to the 9th. If I want to know the force between those two objects, the proton and the electron, what would it be? How could I calculate it? We're going to use Coulombs' law, F equals K, Q1, Q2 divided by D squared, where Q is the charge of an electron and the charge of a proton. I sub everything in exactly how I have it written, 8.99 times 10 to the positive 9th, times negative 1.6 times 10 to the negative 19th, times positive 1.6 times 10 to the negative 19th, that's the charge of an electron and the charge of a proton. Divide that by the distance, the average distance from the electron and the proton, 5.29 times 10 to the negative 11th squared. Again, I want you to practice this, getting all of those numbers into your calculator, not your cell phone, your scientific calculator. If you do that all correctly, you should get a force of negative 8.22 times 10 to the negative 8th newtons. Now, what's up with that negative sign? Before, negative told us a direction, but this time the negative tells us something a little bit different. If I go back to my picture, if I use Coulombs' law, Q1 times Q2, a positive times a positive comes out to be a positive, which means if my force is positive, those objects will repel each other. Same thing, a negative times a negative is a positive. So if my force came out to be positive, those objects repel each other. Lastly, I have a negative object and a positive object. A negative times a positive comes out to be negative. So that means this is an attractive force. I know that those two objects should attract each other, which again was one of the problems we had when we were trying to model the atom. This was one of the problems that not J.J. Thomson had, but that Bohr solved with Rutherford's atom, when Rutherford didn't know why the atom wasn't going to collapse. Now, as a comparison, I would like you, I have some numbers down here, I would like you to try and find the gravitational force between the electron and the proton, and I gave you the numbers you need. Gravitational force depends on mass. The mass of an electron, 9.11 times 10 to the negative 31 kilograms. The mass of a proton, much bigger, 1.67 times 10 to the negative 27 kilograms. The universal gravitational constant, again, is 6.67 times 10 to the negative 11th. And the distance stays the same, 5.29 times 10 to the negative 11th. If you do all of your numbers right, you should get what I have written here in pink. The force of gravity, or the attractive force between those two objects, 3.63 times 10 to the negative 47 newtons. So much smaller than the electrostatic force. So last, to summarize everything, I have just a quick summary of all of Coulombs' law versus Newton's law. Newton's law deals with masses. Newton's law is always attractive. Those are different from Coulombs' law, it deals with charge. And Coulombs' law can attract or repel. Both of them are inversely proportional to the distance squared, which means if the distance gets bigger, the force gets much, much smaller. Newton's law, or the force of attraction between two masses, is very small. We know it's the weakest of the fundamental forces. Coulomb's law, the electrostatic force, is very, very big by comparison to the gravitational force. And the last similarity is they are both measured in newtons. Thanks for watching. Please like, comment, or subscribe, and I will see you next time.